In organic chemistry, we see short-lived species that we call reaction intermediates. These are species that form quickly and are very unstable, so quickly react with something to not exist anymore. These can be formed through processes such as the following. If we treat this molecule here with a base, then we can deprotonate this carbon, giving the electrons from the carbon-hydrogen bond to the carbon, forming a carbanion. Now, this carbanion will have a charge of -1, having a lone pair residing on it. If we look at that, the formal charge will be equal to 4, as carbon is in group 4, minus the electrons which carbon contributes to the Lewis structure. So that's 1, 2, and then 1 for each of these shared bonds. So 1, 2, 3, so -5. Therefore, we end up with a formal charge of -1. Now, in the molecule over here, the carbon sits in the center in a tetrahedral structure bound to our different substituents. This carbon is known as sp3. Now, when the carbanion is formed, this structure still remains the same. We have our tetrahedral structure with the carbon in the middle. We have our same orbitals. Just now we have a lone pair in one of the orbitals, so we draw our arrows in there for those electrons. If instead we have a leaving group on the central carbon, then what we can get happen is that, as the name suggests, the leaving group can leave, taking those electrons with it. The leaving group goes away and we are left with a carbocation. Now this carbocation will have a positive charge, as if we work out the formal charge again, we can see that carbon is in group 4, but only contributes 3 electrons to the Lewis structure now. So we'll have a formal charge of +1. Now, if we look at the geometry of these two structures, just like before, we have a carbon in the center of a tetrahedral structure bound to each of our substituents. Now, unlike before, where our geometry stayed the same, this time, when we turn to our carbocation, we change geometries and we form an sp2 hybridized carbon instead. This is where our molecule is now trigonal planar instead of tetrahedral. We have our 3 R groups bound to our carbon through the 3 sp2 orbitals here. And we have an empty p orbital residing there. Now, if a nucleophile was to attack this carbocation, it could attack from above the plane or it could attack from below the plane. Another reactive intermediate that we can get is a radical. If we have a carbon molecule, as we've seen previously, this time bound to an X. Now this X could be a halogen, it could be a leaving group, could be a H, etc. We can get homolytic fission of this bond, forming our X radical that leaves, we can then form our carbon radical as shown here. Now the formal charge on this one is equal to 4 from our carbon being in group 4 minus the electrons that it contributes to the Lewis structure. So 1 for the unpaired electron here, then 2, 3, 4. So the formal charge on this one will be 0. So as we've seen before, the carbon in the starting molecule is sp3 hybridized. When we form our radical, we get a mixture of sp2 and sp3 hybridization existing in an equilibrium, where we have our R groups bound to the carbon, and then we have our unpaired electron either residing in one of the sp3 orbitals, or alternatively in our sp2 hybridized carbon, our unpaired electron will reside in the p orbital. So these exist in an equilibrium. So as an introduction to our carbene, we'll just look at the structure of it. And in the next video, we'll look at how to make these carbenes. So these carbenes are a carbon with a lone pair, but an overall formal charge of 0. If we look at the formal charge, we can see that we have 1, 2, 3, 4 electrons from the carbon, adding to the Lewis structure, giving us an overall formal charge of 0. So these carbenes are sp2 hybridized, but they can exist in two different states. We can either get the central carbon bound to the two R groups, existing with the lone pair in the sp2 hybrid orbital with an empty p orbital. This is known as the singlet carbene. This comes from our spin multiplicity equation, where our spin multiplicity is equal to 2s plus 1. As we can see, s here is 0 as our spins cancel out. So we've got 2 times 0, which is 0 plus 1, giving us 1, which is where our singlet comes from. Now, these singlet carbenes tend to be the carbenes that we form in solution-based reactions. So they are the carbenes that we will be talking about for the rest of these videos, as when we are doing reactions in the lab, we'll mainly be working in the aqueous phase in solution, and so we will only really see singlet carbenes. The other carbene that can form is known as the triplet carbene. Now we still have our central carbon with our two R groups bound, all still in the sp2 hybridization. Only now we can get one electron residing in the p orbital and one electron residing in the sp2 hybrid orbital. Now this is known as the triplet carbene and mainly appears in gas-based reactions. We'll go through an example of the type of reactions that these triplet carbenes and singlet carbenes undergo to see what different products they might give based off this difference here in the electronic structure. Now, the triplet carbene has a spin of 1 contributing. The s is 1 as we get half from each of these electrons. So 1 overall. So we get 2 times 1, which is 2, plus 1, which is 3, gives us 3. So the triplet carbene. So as I said, we'll look through some examples, but these singlet carbenes mainly generated in solution and react in a concertive way, whereas the triplet carbenes are generated in the gas phase and react in a stepwise manner instead. So we'll look in later videos as how that affects our products.